Hi, my name is Rachel. Thanks for continue watching the tutorial for constructing I/O from well-founded assumptions, and I will tell you about part 2 of the construction. As Amit have mentioned, that our goal is to construct I/O from these 4 well-founded assumptions. And let me start with telling you a bit kind of a high-level bird-eye view on how our construction works. To construct I/O, what we would like to have is to devise a way to encode a program secretly. Yet, given any input, we want to be able to evaluate the input on the program and obtain the output in the clear. There are 2 main challenges towards this task. One is that we want to obfuscate arbitrary programs, meaning that evaluating an input is a rather complex computation and in particular can have very high degree. And coping with this complex computation is difficult. The second challenge is that we are not satisfied with obtaining the output in any encoded form, but rather we really want to have the output in the clear. And this is the second main difficulty. So given that this is what we want and our target, we can ask, what do we have? What can we do? What we can do is that using pairing groups with a bilinear map, we can actually encode the secret elements and evaluate degree 2 polynomials on them and obtain the output in the clear. This is great. However, as you can see that the gap from evaluating degree 2 polynomial to evaluating arbitrarily high degree computation is really large. It turns out that with a lot of intensive effort by prior work, it has been shown that this gap can be bridged if we actually have pseudo-random generator, which is a simple cryptographic tool, shorthand as PRG, that are very simple to compute. In particular, can be computed using degree 2 polynomials. The rationale is that if the PRG has degree 2, then we can really evaluate it inside the bilinear map and obtain the PRG output. And this capability, together with lots of other cryptography tricks and techniques added together, we will be able to get I/O. Unfortunately, we actually don't have degree 2 PRGs. All proposed candidates were broken, and the only unbroken candidates, the simplest ones we have degree 3. On the other hand, with only bilinear maps, we don't know how to securely evaluate degree 3 polynomials over secret elements. Therefore, there is a mismatch, and this bridge of hope does not hold. So what we do in this work is that we actually manage to instantiate PRG that are just slightly more complex than degree 2, which we call degree 2.5 in quotes. And on the other hand, there are ways to evaluate degree 2.5 polynomials using just bilinear maps. Therefore, adding them together with lots of other cryptography, we can get I/O. So hopefully you're now intrigued about what is this degree 2.5 computation. It is computations of the following form. That the computation, actually, the inputs are divided into 2 parts. One is a public part, which we denote as P, and another is a secret part, which denoted as S. So that the computation only has degree 2 depending on the secret part of the input, but however can support more complex, constant degree polynomial evaluated on the public part. This is what we call as degree 2.5 computation. And correspondingly, we can have, so the capability for us to compute degree 2.5 computation using bilinear map is captured by this tool called partially hiding functional encryption. And correspondingly, we can actually construct PRGs that have degree 2.5. We call them structured seed PRG or SPRG. And with them together, we can construct I/O. Okay, so as mentioned, with bilinear map, we can construct partially hiding functional encryption, and we can construct structured PRG using PRG in NC0 and learning parity with noises. We also need additional tools. In particular, using learning with errors assumption, we can get homomorphic encryption for NC0 functions. And these three intermediate tools together will allow us to construct a primitive called functional encryption for computing NC0 functions. Functional encryption turns out to be a very powerful primitive that is essentially equivalent to I/O. From FE for NC0, we will be able to bootstrap or the way rely on prior works to obtain I/O. So in this part 2 of the tutorial, what I will attempt to tell you is that how we can construct this functional encryption for NC0 from these intermediate tools. And then in part 3, that Ayush is going to tell you how to construct the structured PRG that is at the heart of our new construction. Okay, so for the rest of my part of the talk, we're going to focus on part 2. And what we will do is that we're going to gradually develop the ideas towards constructing this functional encryption step by step. And along the way, we're going to introduce these intermediate tools that we use. They themselves are really, really fascinating cryptographic concepts that I really like, and I hope that you will appreciate them as well. Okay, so first thing first, let's start with looking at what are functional encryption and homomorphic encryption. And by comparing these two very powerful encryption schemes, we'll actually get our initial ideas for constructing FE. Okay, so what are encryption schemes? Here, a public key encryption scheme allows us to generate pairs of master public key and secret key. And using the master public key alone, we can encrypt arbitrary message to produce a ciphertext, so that the ciphertext can be decrypted using the master secret key to reveal the encrypted message. And without the master secret key, then the ciphertext reveals no information about the encrypted message whatsoever. For convenience, I'm going to often denote the message being encrypted inside a ciphertext by appending the input X in parentheses behind the ciphertext. And I will also sometimes denote what is the master secret key involved in the encryption as a subscript below the ciphertext. But note that this is only for notational convenience. This does not mean that the ciphertext reveals any information about the input X or the master secret key. In fact, it does not. It hides all information of X and the master secret key. So the security that ciphertext leaks no information about the encrypted input is formalized in cryptography through the language of indistinguishability. We require that the two, given the master public key, ciphertexts of any two different inputs, X0 and X1, are in fact indistinguishable. For most part of the talk, you do not need to understand these formal security definitions in order to understand the ideas behind our construction. So you can just stay with the intuitive understanding that security means ciphertext reveals no information about the encrypted input X. Okay. We sometimes will also consider a different variant, which is a secret key encryption scheme. And this is more or less the same as public key encryption scheme, with the only difference that the encryption, to create the ciphertext, we also need to use the master secret key. Okay, so what is a homomorphic encryption then? Here we consider the secret key variant. And what they enable is that we can compute some function on these encrypted inputs without decrypting ever. So here consider a function that is on an L-bit input and produces an M-bit output, where M could be way larger than the input length L. This graphical representation means that the ciphertext of an input X can be homomorphically manipulated in a way that produces an encryption of the output. Formally, this homomorphic evaluation procedure is performed by what we call the H-eval procedure, which takes the master public key and the function and transforms an input ciphertext encrypting X into an output ciphertext encrypting the output. Again, with a master secret key, one will be able to decrypt this ciphertext and reveal what's encrypted inside. What the security guarantee is that without the master secret key, then the ciphertext really reveals no information about the underlying encrypted message. Note that this holds even if one can homomorphically evaluate lots of different functions and obtain the ciphertext for lots of different outputs. The point is that all these outputs are still encrypted and their ciphertext reveal no information about the input and the outputs alike. And this security notion is again formalized through indistinguishability, requiring that ciphertexts for different inputs remain indistinguishable. On the other hand, let's consider functional encryption, which also extends a vanilla public key encryption scheme to support computation on encrypted inputs. However, it differs from a homomorphic encryption scheme in two main aspects. One aspect is that the crucial difference is that functional encryption not only allows us to compute on the encrypted input, but also allows us to recover the output using a crippled key. These crippled keys are generated using the master secret key together with a particular function, and the producing secret key is what we also call as a functional key and is tied with a particular function. The important part is that when decrypting a ciphertext using this functional key, what we get decrypted out is not the input itself, but rather the output of the function evaluated on the input. Now, the security of the functional encryption guarantees that given the secret key for a function f, only the function as well as the output are revealed, and all other information about the encrypted input that is beyond what the output conveys remain hidden. And this is formalized by requiring that given the master public key and the secret key for f, ciphertext for two different inputs that are not separated by the function in the sense that they have the identical output when evaluated through f remain indistinguishable. Note that if we start with ciphertext for two different inputs that actually produce different outputs, then clearly these two ciphertexts are distinguishable given secret key for f, because one can just evaluate the honest decryption algorithm and obtain different outputs and hence distinguish. That is the intended behavior of the system and does not violate security. Security only guarantees that information about the inputs that is not conveyed through the output of the function remain hidden. Okay. So it might appear at a first glance that functional encryption and homomorphic encryption are somewhat similar because they both support computation on encrypted inputs. However, it turns out the fact that in functional encryption, we can obtain the output in the clear rather than in the encrypted form sets its power to be way higher. It turns out that assuming LWE and PRG in NC0, functional encryption for even very, very simple functions that are in NC0 already implies I/O. So here we do require the functional encryption for NC0 to be somewhat efficient in the sense that the ciphertext size should scale linearly with the length of the input and scale sublinearly with the length of the output of the function. The reason that we require the ciphertext size to be much shorter, sublinear in the output length is that if we are considering only having a single secret key for a single function f, and we allow the ciphertext to be as long as the function output, then one might well just directly give out the function output itself. There isn't that much advantage of giving out a functional encryption ciphertext of the input. And indeed, as soon as we restrict the ciphertext size to be a little bit smaller than the function output, then the functional encryption becomes extremely powerful. And note that here, I am using this slightly weird big O notation, which has a lambda as a subscript. What it means is that not only we will ignore constant factors, we will also ignore polynomial factors in the security parameter lambda. So for the rest of my part of the talk, we're going to focus on constructing functional encryption for NC0. This is now our target because we know it is powerful enough to imply I/O. Okay, so let's put functional encryption and homomorphic encryption side by side. These are really two really fascinating advanced form of encryption scheme. They both allow us to compute on encrypted inputs, with the only difference that homomorphic encryption still obeys the usual all or nothing law of cryptography, in the sense that if someone has the almighty secret key, as here, then he can learn really all information, all secret information about the input, output, whatever, everything that the person knows. On the other hand, if a person does not know the almighty secret key, then absolutely no information is revealed whatsoever. Excuse me. This is what I mean by the all or nothing or 0 or 1 nature of this kind of security goal. It turns out that cryptographers are really well versed in achieving this type of security goal. In particular, in the case of homomorphic encryption, assuming learning with errors, we know how to create homomorphic encryption that can evaluate all functions that can be represented as a polynomial-sized circuits. On the other hand, functional encryption represents a different type of security goal. That is, I would like to give out a secret key that reveals some partial information in the form of a function output y about an encrypted input. And beyond the output, all other information about x is hidden. This capability of give out fine-grained control of what partial information is revealed and the rest being hidden is what is challenging. And essentially, up to now, what we know is using bilinear pairing groups, then we can construct functional encryption for quadratic polynomials. So as you can see, the gap between what we can achieve for functional encryption and for homomorphic encryption is very large. Nevertheless, given homomorphic encryption, a natural idea is trying to leverage the fact that it can support complex computation over encrypted input. The only thing to go to the side of functional encryption is to attempt to decrypt the output ciphertext in a way that reveals only the output inside and nothing else. If we can do that, if we can decrypt homomorphic encryption ciphertexts in a very precise and secure way, then this effectively gives us FE. But the difficulty is, of course, how can we decrypt? in a precise and secure way? Well, we haven't gotten many choices of tools. And one idea is perhaps using functional encryption itself. But this is rather paradoxical because how can we use a functional encryption to construct a functional encryption? That doesn't make much sense. So the hope is that hopefully, in order to decrypt HE ciphertext, we just need a functional encryption for simple computations. And ideally, if we could do decryption using just degree 2 polynomials, then we would be done because we know how to construct FE for degree 2 polynomial using standard bilinear pairing groups. Okay, so with this hope, let's now delve into it and try to start to get more precise. In order to construct the functional encryption for NC0 functions, our initial idea is that we're going to include in its ciphertext some homomorphic encryption scheme ciphertext encrypting the input X. Here, the secret key used for the HE scheme is sampled freshly at each encryption. Then, we would like to use a different, simpler FE scheme and include respectively its ciphertext and secret key in the FE for NC0 ciphertext and secret key. The big question we need to answer is that what is the input and the function we're going to encode using this simpler FE scheme, so that we can achieve our goal that when we decrypt this pair of ciphertext and secret key, what we get is really the output of the function and nothing else. Okay, let's try. One way that we can achieve that is to encrypt inside the simple FE scheme the HE ciphertext together with the HE secret key. And the function H, given these two inputs, is going to first evaluate homomorphically the function f on the HE ciphertext to obtain an HE output ciphertext, and then simply decrypt this output ciphertext using the secret key of HE to reveal the output Y. Well, note that if the functional encryption scheme is secure, it means that the only thing that is revealed through the pair of secret key and ciphertext is the output, namely the output Y. And nothing about the encoded, encrypted secret key S beyond Y is revealed. And therefore, the HE security still holds and hence hides the encrypted input X. So this would indeed be a kind of secure template for us to construct FE. Unfortunately, we need to examine really how simple this function H is. Remember that our motivation is to use a FE scheme for simple functions so that we can kind of start from something simple to go to something more complex, which is for evaluating arbitrary NC0 functions. So how complex is this function H really is? Well, it turns out that at the moment it's rather complex. First of all, the homomorphic evaluation procedure here computes F homomorphically on the ciphertext. And as a result, that the homomorphic evaluation procedure must be more complex than the function F itself. Second, the decryption algorithm of the encryption scheme cannot be too simple because we know that for a secure encryption scheme, its decryption cannot be too simple. For example, it cannot be linear. So it seems that our hope for bootstrapping from a simple FE scheme to something more complex does not really hold. But it turns out that we can cope with the complexity of this function H by using better tools. The first tool we will use is a homomorphic encryption scheme whose decryption algorithm is almost linear. It cannot be linear, however, it can be almost linear, that I will explain shortly what almost mean. And the second is how do we cope with the complexity of the homomorphic evaluation procedure. Well, if we look closely, then we notice that although each eval is rather complex, it is evaluated on the HCT, the HG ciphertext, which is something that we can just reveal. It does not need to be hidden, right? So in other words, what's being encrypted, the encrypted input, contains a public and a secret part. The only thing we want to hide is the secret key for the HG scheme, and we don't care about hiding the HG ciphertext at all. Okay, so therefore this means the function h contains a complex part of the computation that is, however, on public input, and then a rather simple computation that is on the secret input. Interesting. So the hope is that shouldn't only the complexity on the secret input count? Can we actually get computation on the public input part just for free? Then maybe then we can again instantiate this simple FE scheme using bilinear maps. It turns out that the hope is true, and we can actually capture this type of public and secret computation using a new tool called partially hiding functional encryption. Okay, so in the next step, I will tell you about these two new tools, what they are, and then continue to develop our ideas. So partially hiding functional encryption, as the name suggests, is basically functional encryption. However, now it deals with these functions that takes a two-part input. One part of the input is going to be deemed as a public, that does not need to be hidden, and the other part of the input is a secret that needs to be hidden. And when we decrypt ciphertext of this form using functional key, again what we obtain is the output of the function. And the security of partially hiding functional encryption guarantees that, given the secret key, not only that the output is revealed, but also we don't hide the public part of the input. What we hide is additional information about the secret part of the input X that is not conveyed through the output H on A, X. We can again formalize this security notion, this security guarantee, using the language of indistinguishability. However, here we're gonna consider a slightly different formulation through simulation. What it requires is that the master public key, the secret key, and the ciphertext altogether can be simulated using only the public input A together with the output H on A, X. Well, clearly, if this public key, secret key, and the ciphertext can be simulated using only A and the output, then it means that they only convey A and the output and hide all other information about the secret input X. Again, the exact security notion does not hinder understanding the ideas in the construction. Our hope with partially hiding functional encryption is that we want to leverage the fact that the public input does not need to be hidden in order to enable us to support computing somewhat more complex computation on A that is beyond just quadratic polynomials. And indeed, this hope is true. We can actually construct partially hiding functional encryption for degree 2.5 polynomials using bilinear pairing groups. So degree 2.5 polynomials are having the following form, that each of the output elements in the polynomial h, denoted as hi, actually can be written as a quadratic polynomial on the secret input x, where the coefficient of all the quadratic monomials are depending on A through some constant degree computation. In other words, H has constant degree depending on the public input A and has only degree 2 depending on the secret input X. And we refer to this type of polynomial as having degree 2.5, or more precisely, I will say that it has degree order of 1, 2. The public key partially hiding functional encryption scheme that we can construct from pairing groups do satisfy the simulation security, and they also have really good efficiency in the sense that the size of the ciphertext scales linearly with the size of the input. And here, one last caveat that I need to mention is that, as we see, there's a little star here. And the caveat is that it turns out that these partially hiding FE schemes, we can only, when we decrypt, we can only recover the output in the clear if it is the case that the outputs are small, in the sense that they have small polynomial magnitude. And in particular, it would be fine if we're evaluating Boolean functions where the outputs are just 0 and 1. But extending a little bit more, we can also evaluate functions that have larger outputs, but are polynomially sized. Also make an additional note that in the paper that we actually use a secret key partially hiding functional encryption, the difference between secret key and the public key is not significant for our construction. Both versions would work. The only difference is that their implementation will depend on slightly different assumptions of the pairing group. In particular, the secret key partially hiding FE can be based on a different assumption called SXDH in pairing groups. Okay, so the next tool that we need to understand is these homomorphic encryption scheme that have almost linear decryption equations. And they are based on the assumption of learning with errors, LWE. So let me tell you about them. Okay, we all know very well that if we're given with a system of linear equations where the coefficients are random matrix and the unknowns as prime are also sampled at random, then given A and C, we can efficiently solve these linear equations and recover the unknown as prime. What the LWE assumption postulates is that as soon as we perturb the output of the linear system by a little bit using some small Gaussian noises that only have polynomial magnitude, then suddenly that it becomes hard to solve the linear system and recover the unknown as prime. And not only that S prime is hard to find, in fact, it also implies that this A comma C is pseudo-random in the sense it's indistinguishable from A comma R, where R is just a completely random vector. With the learning with errors assumption, we can use it to easily hide some so forgot to mention that for the learning with errors assumption to hold, it is very important that the secret S prime and the noise E remain hidden always. So with learning with errors, we can use it easily to hide input vector by simply adding it to the output of AS prime plus E. And note that once we add it, there's a slight issue that if we get E plus X, in some sense, X and E sort of merge together and we cannot separate them apart anymore. Therefore, we would like to separate E from X. We will actually make the noises even by multiplying with 2. And it turns out that LWE assumptions still hold even if we use even errors. Okay. So this effectively gives us a secret key encryption scheme. We can view the C as the ciphertext for encrypting X, A as the master public key, and the unknown S prime as the master secret key. Note that this encryption scheme is very efficient. The ciphertext length is exactly linear in the input length. Also, the RWE assumption immediately implies that the master public key, together with the ciphertext, note that only one ciphertext is indistinguishable to random. And finally, what about decryption? How can we decrypt? Well, that is also easy. We can simply multiply A, C with minus S prime and 1, and we're going to call this augmented vector secret key S. And this produces 2e plus x, from which we can recover x by simply doing mod 2. Note that this decryption is almost linear, in the sense that with just a linear operation depending on the secret S, we can recover already the encrypted input, however perturbed with some even noise. Furthermore, this simple encryption scheme actually supports homomorphic evaluation for simple NC0 functions. In order to see this, we want to carefully gaze into this almost linear decryption equation. So suppose we're given with an NC0 function. Because it has constant locality, such functions can actually be computed using a degree D polynomial, where D matches exactly the locality over a larger field. So what would happen if we just evaluate the function f on both sides of the equation? On the right-hand side, note that this function f actually contains many output elements, and each of the output elements is some degree D polynomial evaluated on 2e plus x. And this itself is simply evaluating f of I on input x with some additional terms that all depends on e. And all of these terms must be even because the noise is even. And in other words, that we can rewrite this sum as 2 times some other noise, ei prime. And this means that the right-hand side simply equals to f of x plus 2e prime. Well, this is meaning we can get the perturbed output. On the other hand, if we look at the left-hand side, evaluating a degree D polynomial on the product of A, C and S means evaluating a bilinear function on degree D monomials over A, S and degree D monomials over S. Here we write the collection of degree D monomials over a vector Z in the vector form, in the tensor product form of tensoring this vector with itself D times. And similarly for matrices. And going even one step further, we can always write this bilinear function as the product of a matrix CF that depends on degree D monomials over A, C, together with S XOR tensor D times. Now, the left and the right-hand side equal to each other, and this effectively gives us a new decryption equation. And we can simply view this matrix CF as the output ciphertext that is evaluated from A, C using just degree D computation. And the output ciphertext has a slightly bigger dimension than the original ciphertext C. In particular, its dimension is M, the output length, multiplied with the dimension of the secret S to the D. But nevertheless, as long as D is a constant, this dimension is still polynomial and we can compute it. And now the decryption, this almost linear decryption equation is essentially using S tensor D times as the new secret key to decrypt the output ciphertext. Great. So now, additionally, I want to note that the new noise that is encoded in the output ciphertext itself is also a degree D polynomial depending on the original noise in the original ciphertext and the encrypted input. This means that if we want to hide the input X, we really ought to hide E prime. But the saving grace that we will see later is that E prime is actually small as long as the original E and X themselves are small. Here small means that they're polynomially bounded. Now with these new tools of partially hiding FE and HE with almost linear decryption, we can come back to our template FE construction and plug these tools inside. What this means is that the HE ciphertext looks like A times S prime plus 2E plus X. And what we will now encrypt using the partially hiding FE is the HE ciphertext as well as the HE secret key. However, not just HE secret key as is, but actually all of the degree D monomials in it are encrypted as the secret input. Now with these two inputs, the function H can again homomorphically evaluate F to produce the output ciphertext, which is CF. And then now decryption is linear in the sense we just multiply CF with S tensor D times, and that already give us a perturbed output Y plus 2E prime. The good news is that now the function H is indeed simple. It has degree 2.5 because the homomorphic evaluation has exactly the same degree, which is a constant, as the function F to be computed. And the secret part of the computation that depends on the HE secret key is in fact just linear. In addition, that the ciphertext is also very compact. Its size scales with the size of the HE ciphertext, and also the secret key of the HE, which is just some polynomial in the security parameter, and hence the entire ciphertext is linear in the input length. So everything looks really great, except for one security bug. That is, the output of H actually reveals Y plus 2E prime, and hence reveals E prime, which recall that depends on the input X and the original noise in the LWE samples. And this we cannot afford because we want to hide all other information about X beyond the Y. So how can we fix this problem? We cannot attempt to get rid of the noise by modding 2 because mod 2 is a too complex computation to fit into H. The saving grace, as we mentioned before, is that these noise E prime are not too large. They're in fact polynomially bounded. And therefore, a different way of hiding them is to attempt to add to this equation some larger noise rho so that we can smudge the smaller noise E prime. Indeed, if rho is appropriately set, then the statistical distance between the sum of rho plus E prime and the rho itself is rather small, bounded by 1 over lambda, the security parameter. And this way that we can still partially regain security because E prime is now partially hidden. You can effectively think about that E prime is hidden with probability 1 minus 1 over lambda. And furthermore, that we still have correctness. Recall that our partially hiding FE can only recover the output if the output is small. But here, our smudging noise rho is in fact polynomially bounded. Therefore, the entire output is still polynomially bounded and can be correctly recovered. So, putting this idea into effect, what we now want to evaluate using H is the perturbed output adding with the smudge noise 2 times rho. So where do those rho come from? Well, the most straightforward idea is to just encrypt rho as a part of the ciphertext. This way, that we do have that the function H is still very simple, and we also have partially security because E prime will be hidden with good probability. The only problem now is that it actually kills compactness because we need as many smudge noise as the length of the output Y. On the other hand, we want the ciphertext to be much shorter than the output Y. So to fix compactness, our idea is to actually expand the row using a pseudo-random generator so that instead of encrypting row directly, we just need to encrypt the much shorter seed of the PRG so that we can have compactness again. Well, note that now we will have to expand the row through the PRG as part of the computation inside the edge, and therefore the PRG better be really, really simple. So this leads us to our last tool, which is structured seed PRG, and from there we can obtain our final construction. So a PRG is a familiar concept for many, that it allows us to expand a polynomially shorter seed into a pseudo-random output. Here I conveniently denote the seed length to be the output length to 0.99, but in fact, any polynomial, any constant in the exponent that is smaller than 1 will do. More formally, that a family of PRG is defined through 3 algorithms. An index sampling algorithm samples a function index, and then a seed sampling algorithm given the function index samples the seed. And finally, the evaluation algorithm, given both the index and the seed, produces the output. In other words, the PRG that is being computed is the eval algorithm with the function index I. So the security requires that given the function index and the output of the PRG, the output should be indistinguishable from a truly random string. And when we talk about simplicity of the PRG, what we mean is that we want the evaluation algorithm for any function index to be computable by a very low degree polynomial over the Boolean cube. And the quest for such simple PRGs has been ongoing for a long time. And this led to a sequence of really beautiful works that obtains really good candidate degree or constant degree PRGs that is essentially spawned out of Goldrach's PRGs in NC0. On the other hand, in the other extreme, we know that we cannot have linear PRGs. And in addition, we also don't have any good candidates for degree 2 PRGs. This is a bummer because we know that partially hiding FE can only evaluate the quadratic function over the secret inputs. So our remaining hope is that whether we can have a degree 2.5 PRG. And this is what we formalize as structured seed PRGs, which is everything the same as a normal PRG, except that now the seed is divided into 2 parts, a public and a secret part. And the indistinguishability security now requires that even when the public part of the seed is revealed, the PRG output remains pseudo-random. And with the 2-part structured seed, now the evaluation algorithm can have possibly higher computation or more complex computation on the public seed P. And by simplicity now, we mean that it has degree constant on public seed P and quadratic on the secret seed S. I want to note that it is very important to observe that the public and the secret part of the seed are jointly sampled and can be arbitrarily correlated. In particular, this means that though the public seed is public, it is actually not reusable because given P itself, I don't know how to conditionally sample a corresponding secret seed S. And this is the magic of this. This is very much the magic of the structured seed PRG. Previously, there were already some attempts in constructing these degree 2.5 PRGs. However, they all rely on new assumptions. And in this work and in part 3, Ayush is going to tell you how to construct them using learning parity with noises and the PRG in NC0. Unfortunately, we won't be able to construct a full-fledged structured seed PRG, but rather a weaker variant that I will come back to later in the talk. But for now, let's imagine that we have a full-fledged SPRG. And with SPRG, we finally come to our final construction of FE. We can now encrypt both the public and secret seed of the SPRG using the partially hiding FE. The public seed is included in the public part of the input and the secret seed in the secret part. And the function H now will expand the PRG to get a Boolean pseudorandom string R, and then using the bits inside the Boolean pseudorandom string to form those random small polynomial values, row i's. And finally, it can add those smudge noise row i's to the perturbed output in order to hide the noise E prime. As you can see that thanks to the fact that the SPRG has degree 2.5, the function H still has degree 2.5. We also now have restored the compactness because the seed P and S together is still sublinear in length comparing with the output. And let's finally come to arguing about the security. Recall that for security, we would like to show that given the master public key, the secret key, as well as the ciphertext of the scheme, only the output that can be obtained is revealed, and all other information about X remains hidden. And this is captured through indistinguishability in the sense that ciphertexts on these distributions corresponding to one input versus another should remain indistinguishable as long as those two inputs have identical output. Unfortunately, that we won't be able to actually prove full-fledged indistinguishability security, but rather a weak version in the sense that the distributions are not negligibly close, but rather they have a small distinguishing advantage of upper bounded by 1 over lambda, order 1 over lambda. So let's quickly see that how security falls through. Starting with the master public key, secret key, and the ciphertext for one input XP, let's first observe that by the simulation security of the partially hiding FE, these partially hiding FE components reveal only the output of H in the sense that they can be simulated using only the output of H, together with the public part of the input, that is the HE ciphertext. And here, inside the output, the smudge noise row is generated using the structured seed PRG. So next, by the pseudo-randomness of the structured seed PRG, we can swap these smudge noise to truly random ones in an indistinguishable way. And then, as we mentioned before, given that the statistical distance between E plus row is very different from random row itself, with the statistical distance upper bounded by 1 over lambda, we come to a distribution where the noise E prime has disappeared. Once the noise E prime has disappeared, we see that there's nothing that is revealing, no secrets about the HE ciphertext is revealed. And hence, we can rely on the security of the HE scheme to swap the input, replace input XB with simply 0. As such, we can see that the distribution related to input XB actually is indistinguishable to a distribution that is completely independent of XB. And therefore, we can obtain our indistinguishability as desired. As mentioned before, that we actually do not have the full-fledged structured seed PRG, but rather only a weak one. Weak in which sense? Actually, our SPRG only have pseudo-randomness of the output that are not negligibly close, but is only order 1 over lambda indistinguishable from truly random outputs. Nevertheless, combining all these indistinguishability together, we still could prove the indistinguishability, the weak indistinguishability security of the resulting FE for NC0 function. And this comes to brings us back to our overview. What I have just shown you is that we can construct a weak version of FE for NC0, which the indistinguishability security has a rather polynomially small gap. And using previous works, this gives us a FE, full-fledged FE for evaluating polynomial size circuits that also has a rather inverse polynomial large distinguishing gap. And the saving grace is that we can actually use a security amplification technique to boost back the security all the way to negligible indistinguishability, and then it implies IO. Because of the time difference, I won't be able to tell you about the security amplification step. And rather, next we will focus to part 3, that is constructing the weak SPRG from PRG in NC0 and the learning parity with noises. And thank you very much for listening to me.